These notes cover Chapter 1, Section 3 of your textbook. Notice the title to this section, Computing and Problem Solving, not Programming or Coding. The reason is that there is no point to programming a computer unless we are solving some type of problem. We want to keep that in mind. This course is not the mechanics of coding that is so important, but the design and implementation of our solutions that is important. One of the beautiful aspects of the Python language is its focus on the ease of problem solving through its simplified mechanics, also known as the syntax rules. As programmers, we need to think both abstractly, or looking at the big picture, as well as pay attention to details. These are two unique skill sets, and most of us find one easier to master than the other. But we really do need both to be expert programmers. Syntactically, Python is a rather clean language, using less punctuation and symbols than most other languages. This makes it easier to sharpen our abstract thinking skills and focus on elegant solutions to the problems at hand. The programming tools we will be examining here, algorithms, flowcharts, pseudocode, and hierarchy charts, are language neutral. In other words, they are focused on the problem-solving plan. Once we determine that strategy, we can implement the solution via coding in any programming language. An algorithm is a step-by-step set of instructions to solve a problem. It's likely that each of us, in the past week, has used a GPS-guided algorithm to drive from point A to point B. Perhaps you have followed the step-by-step guidelines of a favorite recipe, or have assembled furniture from instructions, or completed a few math problems. All of these are examples of algorithms. We are all pretty good at following them. Now we need to master the art of writing them. The first algorithm example in the text walks us through how to determine the number of first-class stamps we will need for a multiple-page mailing. A good approach to structured programming is to start from an input processing output, or IPO, approach. It guides us from an abstract big picture view into an organized plan for solving the problem. This is a terrific diagram that gives us the big picture at many levels of computing. It fits the bill for how we use the computer in general. We want to be able to provide input to the machine, have it do some work or processing, and produce meaningful, valid output. For example, maybe we want to produce a resume from information we type into a word processor. The diagram also works for producing software or programs, and we will use this simple IPO approach a lot this semester. It's a fine design strategy for organizing the step-by-step instructions for solving the problems we are tasked with. Interestingly, it is advantageous to start by thinking about the right side, or the output. This is the product or outcome we need to achieve. For the snail mail problem, the output is the answer to how many stamps do we need. The next thing to consider is the left side, or what inputs we are given. How many sheets of paper are we putting into that envelope? Finally, we have to consider what processing needs to be done with the inputs in order to produce the output. For our snail mail problem, this is pretty easy. Divide the input number of sheets of paper by 5 to produce the output number of stamps. We also have to remember to round up our result if it is not a whole number. Flowcharts are another visual aid for describing the logic sequence of steps the program needs to make. This helps us formulate the step-by-step process our program will follow. Note that this is a set of diagramming tools that is language neutral. You don't need to be a Python, Java, or C++ expert to read or follow a flowchart, and that is by design. It is often used as a tool for review. We can review the step-by-step problem-solving algorithm before the actual coding begins. Sometimes this review process will involve non-programmers. The review process then helps determine if there are any logic problems to the proposed algorithm. Problems such as, are the steps in the correct order? Are we missing any inputs from what are needed? Do we need more information to solve the problem? All of these can be caught and fixed before a lot of time coding has been wasted. It is easier and neater to find and fix logic errors during the design than once you have started to code, as they frequently will alter more than just a few lines of your program. Here is the step-by-step algorithm solution for snail mail postage stamp problem. Once you understand the meaning behind the symbols, it is easy to determine that this should work. The next step after the review would be to make any revisions needed to the logic and then code the solution. Pseudocode is often used instead of flowcharts when you don't have to present your design to non-programmers for review. It is another way to describe the step-by-step process before coding actually begins. If you take the time to carefully consider and write out your step-by-step solution using either flowcharts or pseudocode before you sit down to code, you are guaranteed to have less trouble coding. Why? Because programming isn't as much mechanical, details of the language, as it is about solving problems. And as you progress through college and into the work world, the problems become bigger and more complex, and the design becomes more important and impactful to the overall success of large software projects. Here is a sample pseudocode for the postage problem. Another tool that is very, very useful once problems get larger is the use of hierarchy charts. These are more abstract. They show the overall program structure, ignoring the specific logic details. A fine starting point for organizing the solution is the IPO, or Input Processing Output approach. Here is an example of the hierarchy chart view of the postage stamp problem. We will make extensive use of these once we tackle larger and more interesting programming problems that are organized into several units. We will use a different style than what is presented in your text. They will be of greater value to us when we get into Chapter 4 topics. The diamond symbol represents a decision point in a program. Another name for decision structure is selection structure. We select one path or another. We will study making decisions in detail in Chapter 3 and use them extensively in our programs. Here is an example of a problem that requires making a decision. A GPS system would need to include this logic for giving directions. Here is the input, processing, output breakdown. and a flowchart for the east-west streets problem. And here is sample pseudocode for the same problem. Notice how the hierarchy mimics the IPO breakdown. This works for a simple problem, the repetition structure allows us to repeat a set of instructions as many times as needed. You will also hear this referred to as looping. We will examine Python's available looping structures in Chapter 3. Note the use of the diamond symbol as part of the repetition flowchart, as we need to decide when to stop repeating the process and, more subtly, whether to even do the process one time. We will explore the logic and mechanics of looping in great detail in Chapter 3. Slides 19 through 23 consider the problem of calculating and reporting the average grade for a class exam. You should carefully review it and the application of the solution design tools presented: input processing output, hierarchy charts, flowcharts, and pseudocode. Get comfortable with them as brainstorming and planning solutions tools. If you take the time to formulate a good design, you will enjoy programming much more and will lay the groundwork for solving larger and more complicated programming problems.